Now that we're done with the circle, we're moving on to arguably my favorite closed shape in all of mathematics, the ellipse. And you'll see why later, why it's my favorite. There's so many really incredible things about this shape that we get just by making this weird slice in a cone. But first thing we need to know is how to even draw it. We know that it's going to be different than a circle. It's kind of like a stretched out circle. And so, unfortunately, since we obviously can't be in class and kind of work through this together, I'm just going to start off with a drawing tutorial. So what you're going to need for this is you might need someone to help you. And you're going to need some kind of closed loop. You can use a chain, a piece of string. Whatever it is, though, you want to make it so it's not very stretchy. It shouldn't have a lot of give. So using a rubber band would be obviously a really bad idea, but something that has very little stretch or none would be really helpful. Like one of those, like a chain for a necklace would be perfect. All right, you're also going to need obviously a piece of paper to draw with. You're going to need 2 points that remain fixed. I stole these magnets out of the office downstairs. They weren't strong enough, so I had to tape them down. What might be helpful is if you can get someone to just put 2 fingers on your piece of paper and then you do the drawing. It'll be a little bit awkward because you're going to run into their arms, but that'll be fine. Anyways, so you're going to pick 2 fixed points. Try to make them a little bit far from each other, and your loop should be big enough so that when you hang it, there's a little bit of sag, right? We don't want this to be like taut in between the two, right? That's technically we could squeeze out an ellipse, but it's going to be really hard to see it. So have a little bit of sag, just like this. Essentially what you're going to do is you're going to take something to write with and keep it around these 2 fixed points. Stretch it so that it becomes kind of taut in between them. And let's hope this doesn't... Well, that doesn't look too great, but I think we can get the idea. Obviously, if I had someone here to hold this down, pretty much met up right there. I think the yarn just kind of waddled off of the magnet a little bit, so it caused it to kind of stretch a little bit too much down here. Anyways, but we got our ellipse. So you'll see it's not a circle, but it is closed and curved like a circle. And perhaps just from the way that we constructed it, you could guess that the center of this ellipse is going to be kind of, all kinds of things. It's going to be halfway between these 2 points, right? But that point, if that is the center of the ellipse, had almost nothing to do with how we drew the ellipse. We use these 2 points to draw our ellipse and some fixed distance, i.e. the string. Anyways, but we'll get to that later. So for right now, first couple of observations. Like a circle, there are an infinite number of diameters through this ellipse, namely an infinite number of lines that are going to go through that center, right? But unlike a circle, they are not all going to be the same length, right? If I were to draw, let's get another color. Can you see that? Not really. I left my colors in the other room. I'm going to go get them. All right, I got my colors. So there are an infinite number of lines that can go through the center of this ellipse, but they're not all going to be the same length. Like in a circle. So this purple line that I drew is clearly going to be shorter than this brown line that I drew across. And they're not all going to be the same length, but we can know that there's going to be one that is the longest and one that is the shortest. This horizontal one, the brown one, is clearly going to be the longest. If we tweak that a little bit, that's when the curve starts to get a little bit more narrow. And so any diameters that aren't this one are going to be shorter than the brown one. The shortest diameter is going to be perpendicular to it, right? It's going to be across the ellipse through the center where the ellipse is the skinniest, right? That is not a very straight line. Anyways, but the blue one is going to be the shortest diameter. The brown one is going to be our longest diameter. I'm going to just throw some jargon at you. For when we're talking about the ellipse, the longest diameter, the one that goes along the wide part of it, we call the major axis. The shortest diameter, this blue line, we call the minor axis. All right, so AC is the major axis, BD is the minor axis, and we call these points AC. The endpoints of the major axis we call the vertices. I don't know why I said it weird like that. The vertices, and B and D are called the co-vertices. Again, this is just some lingo, so that when we use it later, you know what I'm referring to. All right, so two axes, 4 vertices technically, but 2 are real and 2 are co-vertices. But now the next question is, how can we describe this shape? Again, for the circle, it's very easy. It's a set of points that are equidistant from some fixed point we call the center, right? In a circle, all radii are going to be equal. In an ellipse, that is not the case, right? If we call, let's call this center point E, EC is going to be the longest radius, if we can use that term loosely, and EB is going to be the shortest radius. There's going to be a whole range of different lengths of radii. So we can't use radii to define the ellipse. So how can we define it? Well, if we look back at how we constructed this in the first place, we defined it, or we described it, I should say, using these 2 fixed points and some set distance. That is the distance, that is the string that I used. So, this is a little bit cluttered. I'm going to clean it up a little bit. So I cleaned up the ellipse a little bit. I labeled these 2 fixed points F1 and F2. I picked some random point on the ellipse and call that point P. The line, or rather the distance from P to F1, I'm going to call it D1, and the distance from P to F2, I'm calling D2. Now, so the way we want to define what an ellipse is, we could say that it's the set of points whose summed distances, D1 and D2, remains constant with respect to 2 points. Now that was very wordy and off the top of my head, and not very sophisticated. So let's break that down just a little bit. The sum of D1 and D2, it's going to be some fixed distance. I'm going to just call it a constant, or C. The sum of those 2 lines are always going to be the same for any point on our ellipse, which makes sense because, again, the way that we drew the ellipse was using this string. Alright, that's close enough. Alright, so I use this string to describe my ellipse. The distance between F1 and F2 does not change, and so we don't even have to worry about it. D1 and D2 are going to change themselves, but their sum will never change. So if I pick another point, say over here, I'll call this P prime. Let's get a different color. We'll call this D1 prime and D2 prime. Now, if you look at D1 and D1 prime, we can see that D1 has gotten bigger. It's grown as P kind of shifted over here. And D2 shrunk a little bit, right? It was this long and now it's only this long. So while they themselves change, their sum total doesn't change. Because again, I'm sorry, this is going to be equal to D1 prime plus D2 prime. So D1 plus D2 is not going to change. That is going to be a fixed distance. And that is what defines the shape of our ellipse, how wide it is, how squishy it is, or whatever. As I move this around using this fixed distance, the length of the string is not changing. Therefore, D1 and D2 are also not changing. And we can do this for every point on the ellipse. It's true also when we get even down here. So let's call this P double prime. Now you'll notice that the distance from F2 to P double prime is our D2 double prime, and this whole distance is D1 double prime. Okay, so I'm going to relocate that just off to the side a little bit. All right, actually let's label a few other points. So this is P double prime. I'm just going to call this point over here A, whatever. All right, so I'm going to pick some point A. That's going to be the other vertex. P double prime is going to be at my other vertex over here. All right, then we have F1 and F2 in the middle. All right, so D1 double prime is the entire distance from F1 to P double prime. But D2 double prime is the distance from F2 to P double prime. Ooh, almost can't see that. There we go. Right, and so I can just draw it kind of above here. But since they're coincident, it's kind of hard to see, where that is. So I'm going to take this. So again, this is D1 double prime. This is D2 double prime. I'm going to take D2 double prime, and I'm going to just shift it over here, and it's going to fit neatly right here. So what is that fixed distance that is used to define the ellipse? It is the exact distance of the major axis, right? So it's not working perfectly because it's when we deal with matter, it's going to give a little bit. But if I were to just stretch this out, right, it's about the length of the major axis. But the distance between F1 and A is going to be equal to the distance between F2 and the other vertex. So I can just relocate D2 double prime over here, and we can see that this constant isn't just any number, but it is the exact length of the major axis. Ran out of room. All right, so that's the first thing that we want to recognize. How is the ellipse defined? It is defined by a fixed distance, which happens to be the length of the major axis, with respect to these 2 points. Now, I call these points F1 and F2 for a reason, because these are what we call focus points. Focus points are essentially points that help define a curve. We're going to find that all of the conic sections have at least one focus point. Actually, no, scratch that. Every conic section has exactly 2 focus points, and I'll get to that in just a second. So the focus points help define the curve. So now we know how to describe our ellipse. It is defined by a fixed distance, which happens to be the length of the major axis, and it is determined by these 2 focal points. The plural is foci or foci, whatever pronunciation you want. So the ellipse is defined by 2 points, unlike the circle, which is defined by 1. Again, this should sound kind of similar to that of a circle. And in fact, we can use this same exact description to describe a circle. The only thing is, in the case of a circle, our 2 focus points, our 2 foci, are on top of each other. So this one point is F1 and F2. Now if we pick some random point on the circumference, the distance from F1 to P, we'll call that D1, and the distance from P to F2, we'll call that D2. D1 plus D2, am I getting off the board, is some fixed distance. And what that distance is, well, D1 and D2 are both radii. So that fixed distance is just the diameter, or the major axis of the circle. But again, we don't call it a major axis of a circle because all diameters are equal. But I wanted to draw this out just to show the kinship of the circle to the ellipse. A circle is basically an ellipse that hasn't been stretched. Or you can flip that around and you can think of an ellipse as basically a circle that has been stretched, where the center is, or the focus point is duplicated, and the 2 focus points start drifting apart. And if you come up with a good system where you can draw ellipses pretty easily using that string method, you'll see that the further apart the focus points get, the squishier your ellipse is going to be. But the closer your foci get, the closer to a circle you're going to get. And I'll do a quick demonstration of that in just a second to kind of demonstrate that. But this kind of makes sense. Go back to how we got these sections in the first place. If we cut parallel to the base of the cone, we get a circle. If we tilt it just a little bit, we get an ellipse, but that ellipse is pretty circly, right? It's only when we start tilting that plane a lot that section gets stretchier and stretchier and stretchier and begins to look more egg-shaped, more like an ellipse, or easily recognizable as an ellipse. But if these 2 points are right next to each other, it's going to be kind of hard to tell whether it's an ellipse or a circle, right? So this is all to say, just to kind of keep in mind the kinship of the circle to the ellipse and how this makes sense with the cutting plane. A circle is an ellipse where the 2 focus points are on top of each other. Or an ellipse is a circle that has been stretched out a little bit. All right, now I'm going to stop. I'm going to draw a couple more ellipses. with some great difficulty, I managed to draw 2 more ellipses. So you can see this one is much more squishy. The 2 focus points are much further apart. And you can see that as they get further apart, the distance between the focus point and the curve itself, the ellipse itself, gets steadily smaller. But we'll come back to that later with our next comic section. And I actually had to use a longer piece of string for this just to kind of fit the distance. I used the same length for this purple one as I used for the brown one. I used the same piece of string, but you can see the focus points are really close together. The 2 focus points are very close together. Now, if you didn't know that this was an ellipse and you were just looking at it, would you be able to tell that that is not a circle? Probably not. Excuse me. Unless you're an expert geometrician and you know exactly what to do to prove that it's not a circle. Just at first glance, that looks a whole lot like a circle. Because it almost is. If these 2 points were just a little bit closer to the point where they were on top of each other, this would be a circle. But again, as they begin to drift apart, we get a more and more distorted circle or a more and more ellipse. Alright, so we've talked about how to define the curve. I just want to say just a couple more things about the different distances that are involved. Now, for a normal circle, when we have that center, the distance from the center to the circumference, that's the only distance we really need in order to define our circle. But for an ellipse, there are more points and more lines that we need to worry about. If we go back to our first one, we need to know the length of D1 and D2. We need to know the location of focus point 1 and focus point 2, but also somewhere in here is the center of the circle. Between these 2 is the center, sorry, not the center of the circle, the center of the ellipse. Between those 2 points is the center of that ellipse. So once this starts being distorted, we have a multitude of lines and points that we need to keep track of. We still want to keep track of the center, but we also now have 2 focus points to keep track of. We have a few distances to be mindful of as well. And I'm just going to write out a few things about them on this bigger list so it'll be a little bit easier to see. Okay. So I've drawn several lines here and labeled them. We'll just walk through that first thing. All right, so let's start with the blue lines that we're already familiar with. We have this long blue line, which is the major axis, and this shorter vertical blue line, which is the minor axis, and they are perpendicular to each other. I'm calling A half of the minor axis. All right, so 2A is the full minor axis. So A is the minor axis. You can also think of it as the distance from the center to the co-vertex. B, I'm defining as the half of the major axis, right? So this whole thing is 2B. Avoiding any jokes there. So B, you can also think of it as the distance from the center to the vertex, all right? And then F is the last distance that we haven't really treated yet, namely the distance between the focus point and the center, all right? I'm calling that distance F. Now I drew several other lines on here. The lines in purple, I drew from the focus points to the co-vertices, right? And then the brown lines that I labeled the purple lines that are labeled R, and then the brown lines that are labeled C are the distances between the co-vertex to the vertex, right? And those are all 4 going to be equal. Anyway, so you can see there's a lot of symmetry here. All the things are going to be equal. So let's think about some of these distances. We already know that the distance from, essentially 2R is going to define our ellipse. Anyways, we'll get to that in just a second. There are a lot of triangles on here, and since these 2 blue lines are perpendicular to each other, we have a lot of right triangles in this business. So we can just lean on the Pythagorean theorem. Let's first look at this right triangle, A, B, and C. Oh, that sounds familiar. C is clearly the hypotenuse, so A squared plus B squared is equal to C squared. That is not the Pythagorean theorem. That is referring to these lengths. It's true because of the Pythagorean theorem, but it's just coincident. Whatever. Now let's take a look at another right triangle. This one using A, F, and R, right? So that's a right triangle where R is the hypotenuse. So A squared plus F squared is equal to R squared. All right, and as we already said before, these are two of these purple lines essentially define our ellipse. R plus R is our fixed distance. We can also call this 2R. But our fixed distance, as we've already discussed, is the major axis, which is 2B. Right? So twice R is equal to twice B, divide both sides by 2. We can then say that R is equal to B. Now just let that sit for a second. That makes a lot of sense. Half of the major axis, this distance here, is the same distance from, that is the distance from the center to the vertex, is the same distance as the focus point to the co-vertex. That is good to know. So essentially, like, this line is equal to this blue line. Anyway, there are a lot of things we can do with that. Alright, so because this is true, we can then combine these two top equations to get a new one. So R and B are equal, therefore R squared is going to be equal to B squared. So I'm going to rewrite this equation here. A squared plus F squared is equal to B squared. Easy enough. Alright. Then from here, I can subtract A squared from both sides, and we'll get F squared is equal to B squared minus A squared. And this is a helpful thing to know. Because look at the terms that are in this final equation. We have F, which is the distance between the center and the focus point, right? And we have B, which is half of the major axis, and we have A, which is half the minor axis. So this is really good to know. In the future, if we're asked, I don't know, a question like, here's the length of the major and minor axis, find where the center is, right? Or the length from the center to the focus, right? We can find that. If we know the coordinates of these two focus points, and we know these distances A and B, we can then find the distance F, and therefore divine where the center is going to be. We can find the coordinates for that. But that's a little bit later down the road. All right, so for right now, I think that is sufficient. Just exploring some of these general things. Now we want to move on to our second task, namely, how could we graph something like this? Can we come up with an equation that would give us an ellipse?